Africa is a blessed country. Over and above its rich coal resources, it is also well endowed with non-depletable renewable energy sources, notably solar and wind. According to the Carbon Trust, the country has an average of more than 2,500 hours of sunshine per year, and average direct solar radiation levels range between 4.5 and 6.5 kilowatt hours per meter squared per day, placing it in the top 3 in the world. Since 1994, there's been a significant number of households that have been electrified by Eskom. Rural electrification rates are atypically high, at 77% nationally, compared to an average of 17% for sub-Saharan Africa. Expectations of grid connection and quality of service are therefore high. However, there's still an estimated in excess of 3 million people without electricity in rural and remote areas. Several challenges prevent electrification of the remainder of deeply rural parts of the country. These include the high cost of grid extension of the network to remote areas, the current low income levels of these communities, low density of rural populations, and difficult terrain conditions. Eskom regards microgrid applications as suitable for these geographical locations that are far, difficult, and expensive to reach. A microgrid is a group of interconnected loads and grouping of electricity sources such as distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid that can disconnect and function autonomously depending on the situation.
This project, the rural microgrid that's now based in Vicksburg, talks a lot with respect to poverty eradication and universal access to electricity. The system has been built for fit-for-purpose microgrids. So the energy requirements on the system has been taken into consideration when designing the system. And the system has the capability to be rapidly redeployed or added on to should the requirements be available.
The system itself, when we design it, comprises of 3 criteria. That would be to be modular, reliable and sustainable.
The Free State demonstration plant is made up of a number of traditional energy components coupled to advanced control systems and technologies. The plant harnesses solar energy and converts this to a peak of 32 kilowatt electrical energy via photovoltaic panels and power inverters. This energy is utilized in 2 ways. The first part of the PV energy is converted from direct current to 220 volts alternating current at 50 Hz frequency. This is the standard low voltage supply presented to residential customers. The remaining energy from the PV panels is stored in 3 sets of lithium-ion batteries, totaling 90 kilowatt hours of storage. This storage is used to supply the inverters when low or no sunlight is available to the PV panels. The inverter once again transforms the stored DC battery energy to 220 volts of AC electrical energy as a supply to the customer. There are many new technologies being demonstrated within this pilot. Firstly, the communication system that is used to manage the homes and the plant comprises of a hybrid radio frequency or wireless system that is meshed to a power line communication technology. This hybrid system provides optimal communication for the control and operation of the plant. The highest level of cybersecurity has been incorporated into the design to prevent unauthorized access and cyber attacks. This communication system forms the backbone for other auxiliary systems such as physical security systems using IP cameras and remote monitoring with intruder detection and alarming, advanced metering infrastructure and smart prepaid metering systems utilizing energy balancing, theft and tamper detection, appliance control and home automation systems for active load control and energy management.
The research shows that just by providing basic energy for lighting and for refrigeration, as well as for basic entertainment and charging of cell phones, has got a huge impact on socially uplifting a community.
Eskom's climate change strategy has a sustainable development approach, which means we try to meet the aspects of socio-economic development, affordability, economic growth for the country, as well as, of course, the environmental aspects. So a project such as a microgrid project ticks all of those boxes in many ways, and for us it's a very exciting opportunity. So in the socio-economic aspects of the project, we have the community involved in development, in understanding what is going on, in being a fit-for-purpose plant, so that the plant meets what the community wants rather than us dictating a solution. Affordability is also a very important aspect given the development of the country, the development status of the country, so that aspect is also being covered through this project.
Mosebetsi ona o ntsong o etsahala sebakeng sena sa rona go thabetse haholo. O fetetse maphelo a rona re se re bone ka ho nka bana ba rona ba nentse ba dutse ba sena mesebetsi. Mosebetsi ona o etsahalang mona sebakeng sa rona e leng Belemina ke mosebetsi o go thabetseng haholo re le bahai ba Belemina mona.
Ke ikutlwa ke le motlotlo haholo ha ile mona Eskom e tlo re kenyetsa motlakase gore re dule ka hara kganya gobane ne re dutse ka hara lefifi mme ne re tshwenya ka hara lefifi leo le ne re le ka hara lona petsi jwale mme ke motlotlo haholo ka se etsahalang mona kabelo ka rona.
All this information is fed live to the Smart Grid Visualization Control Room. This is based at the Eskom Research, Testing and Demonstration Building in Rocheville, Johannesburg. The Smart Grid Visualization Server uses live feeds such as weather and fire information to predict the performance of the plant related to storms and can preempt physical threats such as lightning and fires ahead of time. The ultimate aim of any smart system is to be preemptive rather than reactive. Therefore, the system must act ahead of time of a problem rather than after the fault has occurred, thus reducing SAIDI and SAFE on the network. Microgrids are modular, fast, deployable energy solutions. The fit-for-purpose design allows for the optimal mix of technologies to manage supply and demand effectively and efficiently. There is minimal impact on the physical environment. Eskom regards microgrid applications as a suitable generation technology where electricity is currently not provided. Other areas in which microgrids can be deployed are usually similar to the pilot, namely sites in which communities have little or no access to electrical energy and where the cost or effort of extending the national grid to reach them is prohibitive based on geographical locations that are far, difficult and expensive to reach. Each site needs to be assessed to determine if socially and economically whether a microgrid is the best solution for that specific location. Locations of a community deep in a sparsely populated area or high in the mountains or far from the grid are all good candidates for a microgrid deployment.